All right. Welcome to the breakfast bash. Let me mute myself. Today we'll be talking about like another data structure. So last week we talked about stacks. Today we're going to talk about queues, which are in many ways very similar to stacks. The difference is that a queue, when you push something onto a stack, it goes to the top. And when you pop something off of the stack, you take it from the top. So we call that a first in, last out type of data structure, because the first thing that you put into a stack is the last thing that comes out. A queue, on the other hand, is what we call a first in, first out data structure. So this means that when we push something onto a queue, it's the first thing to come out. So there's really only one difference between stacks and queues, and that's it. Instead of pushing things onto the top of, so in a queue we have like a back and a front, and instead of pushing things onto the front and popping from the front, we push things onto the back and pop from the front. So that might make a little bit more sense in a second. This is an example of a queue. At the back we have 1, and then we have a 17, and at the front we have 6. And basically we can see a visual representation of a queue in this way. And then we have 2 operations, the first of which is enqueue. And what enqueue does is, so before we had 117.6 as our queue, and enqueue, when we enqueue 99, it goes to the back, and we move the pointer, the back pointer, to point to this element. And that's it. And then the other operation that we have is dequeue. And dequeue, what dequeue does is, before we had 117.6, and now we have dequeuing, we pop off the front, so we get 6 back, and we move the front pointer back to this 17 node that we had previously here. And that's it. So we push to the back and we pop from the front, and that's all that a queue is. And with that, I think we can get started on the application for the week. So this application that I'm going to talk about is very pertinent to 3D or 2D graphics. I'm sorry. So with applications like Paint and Photoshop and stuff like this, this algorithm that I'm going to present is probably used somewhere in there, or some form of it at least. And the application is flood fill. So the goal here is going to be to fill this space with a green color. That's what we're going to do. But we don't want to step over these boundaries here. So you can imagine that you have a picture here, and this is like a picture, and we want to use like the paint bucket tool on this area and turn it green. So that's what we're going to do. And the idea using a queue is very simple. So you're going to start at a cell and then color it whatever color you want to color it. So we'll color it green. And then we're going to look at the surrounding cells, the 4 around it, if they exist. And if they haven't been queued up yet, and they're not black, like if they're the target color that we're looking for, this pink-ish color, we're going to enqueue them. And on every step, we're going to pop off of the queue and color it, and then enqueue its neighbors until the queue is empty. And so I'm going to walk through an example of this, just to hopefully make it clear what we're doing, because I know just talking about the idea doesn't really help too much, but the basic idea is process a cell and then queue its other cells for processing, queue its surrounding cells for processing. So the first step we're going to do, so we're going to start at this cell. And like I said, so we're going to take this cell, color it green, and then we're going to look at its neighbors here. And I'm going to label them by iteration. So this is the first iteration of the flood fill algorithm. And we're going to process these things in a counterclockwise way. So like we're gonna add this to the queue, then this to the queue, and then this to the queue, if that makes sense. And that'll become important in a minute, but it's sort of arbitrary the way that I'm doing it. I'm just kind of doing that for consistency. But anyway, so we enqueue this, we enqueue this, we enqueue this, and we end up with this queue that we need to process on the next iteration. And so this is what I was talking about. So we're going to start at the top here, and what we're going to do is we pop off that one there, and now we're processing it. So we're going to color it green, and then we're going to look at its neighbors that we haven't processed yet, and we're going to shove them onto the queue. So in a second, we're going to see what that looks like. So we color this one green, and then we add these two onto the queue. And then we pop off again. So we went from here. We're going to get that next one. So we have this next one here. We're going to look at that. We've already enqueued this neighbor. The only one left is this one. And this one's black, so we're not going to enqueue it. And we're going to color that green. And then we're going to push that 3 onto the back of the queue. And now we're left with this queue, 3, 2, 2. And we're going to pop off that last one there, right down at the bottom, and enqueue its neighbors. We've already seen the 3, so we're not going to re-enqueue that, but we haven't seen this 4 yet, so we're going to put that at the back now. And so at this point now we've gone through the original 3 neighbors of the first cell that we looked at, and as you can see, like we're kind of going outwards here. So this was the first one that we enqueued, and this was the start of the second iteration of the flood fill algorithm that we went through. So so we enqueued this one next. So we're going to pop that off and color it green and enqueue its neighbors. So this one only has one that hasn't been processed, and we'll label it 5. So now we have 5 at the back, and then we have 4, 3, and the other 2 here we're going to process. We're going to color it green and enqueue its other neighbor, 6. The 1 has already been processed, and the 5 is already enqueued. So we're going to push that 6. Now we have 6, 5, 4, and we're looking at this 3 now. And we're going to color it green, enqueue its neighbors, and so on. So at this point, actually, when we pop off the 4, there's nothing else to enqueue. So this is interesting because we're not lengthening the queue anymore. That's it. So then we're going to color this 4, and we're going to push nothing. And so now our queue is just that 7 and the 6 that we had before, and we're looking at the 5. So we color that green and enqueue its neighbors, and this one still does have one more neighbor to process. And we're going to push that 8 on. And now we've got 8, 7. We're looking at the 6. Color that 6. And we're going to color the 7. And then we're going to color the 8. And that's it. So once we process the 8, there was nothing left to enqueue. There was nothing left in the queue. This is it. So we're done. And that's it. That's basically, there's an interesting variant of the flood fill that uses recursion. And that's sort of interesting from a theoretical perspective because queues can be used in some instances to do to turn recursive algorithms into non-recursive algorithms, which is exactly what we did here. And the last thing that I'll end on is that this flood fill algorithm is in some way a special case of a breadth first search. So a breadth first search on a graph is going to look very similar to this algorithm that we just presented. And I encourage anybody interested to look that up and see what that's all about as well. But I'm not going to go into it in detail here. I just wanted to mention it in passing. That's all I've got. That's queues and flood fill. So thanks, guys.
Awesome. Thanks, Ben.
Travis, I was muted, buddy. What's up?
Oh, I said thanks. That was amazing.
Oh, yeah. All right. Thank you.